All right, guys, we're up to the product and quotient of complex numbers, and I'm going to prove the product rule in this case for complex numbers. If you remember the sum of two angles, trig identity, sine, cosine, cosine, sine, cosine, cosine, sine, sine. I know if you forgot it a little bit, hopefully it's back in your head again. All right, so let's get to it. The very first thing we're looking at is Z1 and Z2. Z1 is a complex number in polar form. Z2 is another complex number in polar form. Notice R1 and R2 are two different radii. Theta 1 is one angle and theta 2 is another angle. So those are two different complex numbers. Okay? What if we were to multiply them? Let's give it a try. Let's prove this thing. So if I were to multiply the two complex numbers in polar form, well, actually, before we do that, imagine if you had to multiply these numbers. Whoops. This and this. You'd have some distribution, right? 1 times -3, 1 times -4i, -√3i times -3, -√3i times -4i. And what if you had more multiplication to do? So instead of multiplying just two complex numbers, 3 complex numbers, 4 complex numbers, if you imagine like x plus 1 times x plus 2, hey, not a big deal. But what if you do x plus 1 times x plus 2 times 2x minus 3, and then take that and multiply by x plus 7, right? That's that binomial repeated multiplication. We've had binomial theorem to figure that stuff out, and Pascal's triangle and all those things. But in this case, we have a better rule for how to multiply complex numbers besides just brute force doing distributive property over and over and over again, especially when it becomes a product of more than two binomials. And this is where polar form just blew my mind. It's really cool once we apply it, because you'll see how much easier it is to do complex number complex number multiplication and division, because addition and subtraction are super easy. Take a look at example 1. Right over there. Right? Addition and subtraction are super easy, but multiplication, not so much. So let's prove this. So if I take Z1 and Z2 and I multiply them, the first thing we're going to do is multiply the radius. Here, whoops, multiply that and that, right? So I can just say it's R1 times R2. But then we have some distributive property. I got to distribute cosine theta 1 to each one of those, right? And so I'm going to have cosine theta 1 times cosine theta 2, right? And then I'm going to have cosine theta 1 times I sine theta 2. So I'm actually going to write it like this, plus I sine theta 2 cosine theta 1. So that's just multiplying it out. Let's multiply this over to each one of those. And so if I have I sine theta 1 cosine theta 2, right, that's going to be plus I sine theta 1 times cosine theta 2, and then plus I squared sine theta 1 sine theta 2. So you know how that math works. And a couple of things we can highlight here. I squared, a little bit of review. I is square root of -1, so I squared is root -1 times root -1, which means it's -1. So that can just be a -1. We've seen that before in earlier chapters and in previous math, and I will go over the cycles of I, which blew my mind once I looked at complex numbers in polar form later in the section. But right now, I squared is -1. We've seen that before. So let's simplify everything. So this is still R1 times R2. Notice if this part is negative sine theta 1 sine theta 2, I'm going to group it with group it with these. I'm going to keep these grouped together. So this is going to be cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, right? So those are this and this put together. And then, sorry, this and this. Now I'm going to take this and put it in, but I'm going to factor out that I. So plus I sine theta 2 cosine theta 1. Again, factoring out the I. So plus sine theta 1 cosine theta 2. And hey, do you notice something? Cosine minus sine, right? Cosine, sine. What trig function does that come from? Comes from the sum of two angles of theta 1, theta 2 of cosine. And you see a minus, that means you should see a sum as your argument. So cosine of theta 1 plus theta 2, right? And then plus I, and I go sine, cosine. Whoops. So this part, if you switch it around, it goes sine, cosine, sine, right? Because multiplication order doesn't matter. So that ends up being the sum of two angles for a sine function. So sine of theta 1 plus theta 2. Again, addition doesn't matter the order, so I can say it's theta 2 plus theta 1 or theta 1 plus theta 2. And there is your rule, right? So what is this thing saying? It's actually saying something really simple. In polar form, if you have two complex numbers in polar form, it is ridiculously easy to multiply them. All you have to do is take each radius here and here, and you multiply them. What do you do with their two angles? Add them. And that's it. Instead of having to do distribution over and over, all you have to do is add the angles and multiply the radii, and that's it. For quotient, you just do the opposite. You divide and you subtract the angles. Again, really simplifies the mathematics of product and quotient, and later on in the section, powers and roots. So I'll do a few examples in terms of just seeing you being able to visualize this new formula that we're going to leverage to see these new patterns and not just blindly distribute binomials that take forever to do. I'll see you in the next examples.